In this chapter, we will be continuing your study of trigonometry. In this lesson, we'll look at oblique triangles using something called the sine law.
All right, hi everybody. Now, at this point here, the material that we look at here in trigonometry, it takes kind of a different turn. We're kind of done exploring what trigonometry looks like on the coordinate plane. Now we're going to take a look at a different application of trigonometry here. We're going to look at what happens when you're working with trigonometry and triangles that aren't right-angled triangles. Okay? So, for example, take a look at what we've got here. Whoops. Take a look at this triangle right here, ABC. Now, ABC might look like a right-angle triangle. It might look like that angle ABC is close to a right angle, but it's not. It's a little less than that. So the question is, how would we use trigonometry to help us work with a triangle that's not a right-angle triangle, what we might call an oblique triangle? Okay? Well, what we do, probably what you can guess by the diagram here, we're going to drop an altitude, okay, H. And H is going to be perpendicular to that side AC. Now, the benefit of that is that all of a sudden it creates two right-angle triangles. And so we are right back to basic trigonometry the way you know it. Now, here's where the sine law comes from. If you take a quick look right here, hopefully I got everything in the screen here. If you look at this triangle right here, just ignore, here, let's cover this one up here. If you ignore that, take a look at this. The sine of angle A is going to be the side H over C. So sine of A is H over C, okay? And with that, I can do a little bit of, if you want to think of it like this, you can think of it as cross multiplying. 1 times H, C times the sine of A, okay? So H is equal to C times the sine of A. Or, look at it like this, just look at this triangle, and we see that the sine of C is going to be H over little a here. And again, if you cross multiply here, multiply up by the A, H is equal to A sine C. Okay? Now, if that's true, okay, then both of those are equal to each other, okay, because both of these expressions are equal to H, then we can set them equal to each other. And then by simply dividing both sides by C and both sides by A, I can create this relationship here, or sorry, this one or this one right here. In other words, the sine of C over C is equal to the sine of angle A over the length of side A. Okay, or you can find the reciprocals there. Now, we could do the same thing with a different set of angles. Like we could have done it with angle A and B, and we would have gotten that the sine of A over little a was equal to the sine of B over side B. And this gets us the law of sines, okay, or the sine law. In any triangle, if you compare the length of a side, okay, divide that by the sine of the angle opposite it, that ratio will be the same for all three pairs of sides and angles that you can create in a triangle. Okay, and that's the law of sines, or what we call the sine law. And so if you know, okay, let's say for example, you know side A and angle A, and you know one of those two, you should be able to figure out the other. Now, this particular rule does come with a little issue, okay, a little problem here. Here's the issue here, that remember sine is positive in two quadrants, okay? That's quadrants 1 and 2. Now, it turns out, if you've got an angle in quadrant 1, that's an acute angle. That's not a problem. Not a problem at all. If you've got an angle in quadrant 2, that's an obtuse angle, which is also not a problem. It is totally possible to have a triangle that's got an obtuse angle in it. Now, if it does, it's only got the one angle. But here's where we run into a little bit of problems here. Sometimes, given the information that you've got, when you apply the law of sines here, sometimes you're not quite sure which angle they're referring to. Are they referring to the acute angle or to the obtuse angle? Because remember, we've looked at this already in the past here, that it is possible, okay, for two angles to have the exact same sine value. And so when you're solving for an angle, sometimes you can't tell. And we call this the ambiguous case of the sine law. When there are two possible triangles that you could create based on the information that you're given. Now, we are going to go through and just start to crank through some examples applying the sine law, okay? And you're going to see how I handle that two possible triangle situation here. In fact, as we go through this, you're going to see basically every possible scenario that we could throw at you. So please just pay attention to the way the questions kind of unfold, how we unpack them as we go through the next few examples. All right, here we go. In triangle DEF, angle E is 48 degrees, side E is 9, side D is 11. We're going to find angle D to the nearest degree. Okay, so let's just draw this out here. E, D, F. E is 48 degrees, good. Little e or side E, which will be opposite that, will be 9. D will be 11, and we are looking for angle D. Okay, well, this is clearly a sine law problem. I can see that because I know this angle, and I also know the side opposite that. As soon as I get a pair like that, I know that I can use the sine law. So I'm going to set this up here as 9 over the sine of 48 degrees. And if I'm going to, the only other bit of information I have here is little d. So the other pair that this is going to be equal to will be little d. Sorry, I don't know why I was about to write little d. I'm going to write 11 over the sine of angle d. Now what's convenient about that is I am looking for angle d. Okay. Now I've got a fraction equal to a fraction, so I've got this proportion here, so I can do this little cross multiplication here. Okay, and it's almost always the case when you cross multiply, then you divide. I'm looking for sine d, so I'm going to divide by 9, so this will be 11 sine of 48 degrees divided by 9. Okay, go to my calculator. And this is going to be 11, 11 sine of 48. Now, it's a really common mistake to forget to close the brackets here. If you don't close the brackets, then you're going to be taking the sine of the wrong thing. You're going to be taking the sine of 48 degrees divided by 9. So you got to close the brackets there and then divide this by 9. Okay, I'm going to press enter, and I get this sine of d is equal to 0.9082812 and so on. Now, I don't really need to write it out like this. I mean, I can just use the calculator to give me this right here. But the reason I write it out like this is because right now I want to stop and just take a look at where I'm at right now. Just ignore what has come before this, okay? Completely ignore it. What I want you to see here is look at this problem and recognize that we've done this before. Okay, we've done problems like this before. Sine is positive. Well, I know that sine is positive in quadrants 1 and 2. So I'm looking for either that angle right there or that angle right there. So what I need to do first of all, is find the reference angle or the angle inside the triangle here. Now, I'm running out of room here at the bottom here, but whatever. So that's going to be the inverse sine of 0.9082812 and so on. Now, I'm just going to do it like this. I'm just going to press second sine, and then second, and then right here above my negative symbol there is the answer. And that's going to take that number that I just calculated here and plug that in there as my answer. And when I do that, I get 65 degrees. Now, granted, I got to round that to the nearest degree, but I'm okay with that right now. So it's 65 degrees. Now, here's the thing. That is the angle inside the triangle, but that triangle could be in the first quadrant or the second quadrant. So the angle D that I'm looking for, D, could have been 65 degrees, or it could have been 180 minus 65 degrees. Think about how we found that in the second quadrant. It means D could have been 65 or 115 degrees. Well, which one is it? So here we run into a situation where this could actually be the ambiguous case of the sine law, that issue that I was just talking about a few minutes ago. Is it possible that both of those, or either one of those, could work? Well, let's just take a quick look here and compare them. Because one of the things we know is that the angles in a triangle should add up to 180. So if it was 65 degrees, if angle D was 65 degrees, I already know from the question that E was 48. Okay? So let's just think about this. Okay? If D is 65 and E is 48, then what I'm going to do is I'm going to subtract both of those from 180 to see what would be left over. And if that's the case here, angle F would be 67 degrees. Okay, well that makes perfect sense. Those angles, totally, I could see that in a triangle easily. Now let's go over here. What if angle D was 115 degrees? Well, I can't change angle E. That was the angle that was given to me in the problem. I don't have any say over that. Okay, but does it make sense? If I've got 115 degrees here, can I subtract that from 180? And can I also subtract this E angle here? And when I do, that gives me an angle of 17 for angle F. Okay, do those angles make sense? Well, yeah, I mean, this is a little small, but that's totally okay. That's totally fine. So what this means here is there are, in fact, two possible ways that this triangle that they're trying to describe could be drawn based on the information that I'm given. This is the ambiguous case. Now, you're going to see in a little while here scenarios where this wouldn't work, okay? But for right now, just understand what I'm trying to do here. When I solved that trig equation with the sine, there were two possible answers there. I was given another angle here. So with each of those angles that I was able to calculate for D, I'm going to try to figure out what the third angle would be, and I'm going to evaluate that. If these angles make sense in the context of a triangle, if they both make sense, then I've got the ambiguous case here. I don't know which triangle they actually meant. Okay, there's not enough information to tell. But you're going to see in a little while here an example where that isn't the case, and you can tell clearly which one was the intended question here. Let's keep going. Okay, now in this question, we're going to be asked to solve the triangle, and that means find all the missing sides and angles here. Now, usually to do this, you need to be given 3 different bits of information to find the remaining 3 bits of information here. Then the rest of this question simply tells us how to round it. Angles to the nearest degree, sides to the nearest tenth. Okay. So we're going to take a look at triangle XYZ. So let's just draw this out. XYZ. Okay. We know that Z is 33 degrees. Angle Y is 112 degrees. Now I didn't really write that to scale, but whatever. And then side Z is going to be 28. Okay. Now, first and foremost, it should be pretty obvious to me that I can figure out what angle X is without putting any effort into this whatsoever. All I got to do is subtract 112 and 33 from 180. All those angles should add up to 180. Now, it's surprising to me how many times people forget that. Okay, and then they stumble on a question like this because they forget that easy little first step there, and then you can't make any headway if you don't have that answer there. So when we subtract those from it, we're going to get that angle X is 35 degrees. Okay. So there we go. Now we got to find the sides little y and little x here. Because we're given enough information there to figure out what y is, we'll figure out what little y is first, and we're going to have to use the sine law. I know that I have to use the sine law because I'm given the side angle pair for z. So we know that 28 over the sine of z is going to equal y over the sine of 112 degrees. Okay, now I've got a proportion here, fraction equal to a fraction. I'm going to cross multiply. 28 times the sine of 112 degrees is going to equal y multiplied by the sine of 33 degrees. And then, just as it is with almost every case when I have to do cross multiplication, I'm going to divide by the sine of 33. So 28 multiplied by the sine of 112 divided by the sine of 33 degrees is going to equal y. I'm going to go to the calculator now. Okay, see, I'm trying to avoid that glare there. Anyway, 28 multiplied by the sine of 112, make sure you close the brackets there, divided by the sine of 33. And what do we get? We get 47.66. Okay, so 47.7. Supposed to round sides to the nearest tenth. 47.7 units, whatever that is. Okay, so there's y. Now I got to find x, and we'll do the exact same thing. Now notice I can't use the Pythagorean theorem, okay, because this isn't a right angle triangle. There is no hypotenuse. Okay, now granted, y here is going to be the longest side in this triangle because it's opposite the largest angle. Okay, and you should notice here that the smallest angle is opposite the smallest side. You should use that, kind of think about that, okay? Kind of helps you judge whether you're on the right track or not, whether you've calculated things correctly. But this is not the hypotenuse. Please bear that in mind. Now let's come over here, and we're going to use the sine law again. So sine of 28 over 33 degrees, because I know that ratio, is going to equal little x over the sine, and I determined that x, capital X, was 35 degrees. Okay, so now we're going to cross multiply there. So 28 multiplied by the sine of 35 degrees will equal little x times the sine of 33 degrees. And then we're going to divide. So 28 sine of 35 degrees over the sine of 33 degrees. Now you should notice this little pattern of set up the ratio, cross multiply, divide. Set up the ratio, cross multiply, and divide. In fact, the only time that we're going to vary from that is when we're looking for an angle, and the only reason we vary for that is when we do at the very end, after we've done this calculation here, we'll go second sine to get the angle. That's it. That's the only difference here. So this is going to be 28 sine of 35, close brackets, divided by the sine of 33. Okay, and we're going to get that the little x value there is going to be 29.5. Now, just to be sure, okay, x here is kind of the middle angle here of the three, so little x should be the middle side. Okay, y is 47.7. Okay, that's big. 29.5. Well, what was little y? Little y was 28. Okay, good. So little x here, my side x, is slightly bigger than side z, which is what I would expect because their angles are pretty close to each other, but this one is a little bit bigger. Perfect. Okay, let's take a look at another one here. So triangle ABC. Okay, so here we go, ABC. A is 43 degrees, little c is 28.5, and little a is 36.1. Okay, and we want to find angle C to the nearest degree. Okay, well I know I'm going to use the sine law because I've got this angle and the side pair. So I'm going to set up that ratio, 36.1 over the sine, of 43 degrees is going to equal 28.5 over the sine of C. Okay, now I'm looking for an angle. So even right now I'm thinking, this could be an ambiguous case here. Okay, I'm likely going to end up with two options here. So I'm going to cross multiply 36.1 times the sine of C will equal 28.5 times the sine of 43. And then just like I've done a couple times already, I'm going to divide by that 36.1 and I'm going to get 28.5 sine of 43 degrees over 36.1. Okay, so now that is going to be 28.5 sine of 43, making sure I close that set of brackets, divided by 36.1. 36.1. There we go. Okay, so there's the ratio there. So the sine of C is going to equal 0.538419757.9, and it's going to go on and on. And again, I write that out like that because not that I needed to. I'm going to let the calculator remember that number anyway. But so that I can look at this right here and think, okay, I'm getting this decimal. Sine of C is equal to some number. It's positive. So I could have a first quadrant or a second quadrant angle. First thing I got to do is I got to figure out what the size of that angle is by taking the inverse sine of 0.5384, so on and so forth. So now I'm going to take the inverse sine of that answer, and to the nearest degree, I'm going to get 33 degrees. Okay, now, but I don't know whether the intention here was that be a first quadrant angle or a second quadrant angle or both. Okay? So where I'm at here is that angle C, okay, angle C could have been 33 degrees in the first quadrant, okay? But it also could have been in the second quadrant, in which case I just subtract 33 from 180. Could have been 47 degrees. Now, let's take a look at angles A and B, because these are how I'm going to determine whether or not these are both acceptable or only one of them is acceptable here. Now, angle A I had no say over. Angle A was given to me to be 43 degrees. Okay. So now, let's just go down and take a look at those two right there. Is it possible, does it work, that I could have a triangle that's got those two angles in it? Well, let's see what they leave me. If you take 43 and 33 from 180, you are left with angle B being 104 degrees. Yeah, not a problem with that. That's fine. Okay, now, but what if it wasn't that? Let's take 147 and 43 and subtract them from 180. That leaves us an angle of negative 10 degrees for B. Say what? Okay, that doesn't make much sense. I can't have a triangle that's got a negative angle in it. That doesn't make any sense here. So what that means is that option right there, that 147, is no option at all. There is only one possible triangle here, so there's no ambiguous case. Okay? There's no ambiguity in this problem. The answer here has to be 33, 43, 104 degrees. That's it. So the only possible answer for angle C is 33. All right, let's try another one. Angle GHI. Okay, let's just draw it out. Okay, angle GHI. All right, G is 50 degrees, little g is 17, little I is 25, and we're going to find angle I. Now notice this is identical really to the problem that we just did in terms of the information that we're given. Once again, it's the angle that I'm looking for here. So again, there's this possibility of the ambiguous case popping up where there might be two possible answers here. Let's have a look. So I know it's going to be the sine law because I've got this angle side pair that I can work with here. 25 over the sine of I. All right. Now, same as before, I'm going to cross multiply. Okay, cross multiply and then divide over 17. And so the sine of I is going to be, just got to go to my calculator here. Now you've seen me do this a couple of times already. Please just make sure when you do this that you're closing the brackets. I keep saying that because I want you to remember that that's an important step there. And I'm going to get the sine of I is 1.12653, and it just goes on and on. Okay, so that could happen, okay, in quadrants 1 or 2. So I'm either looking for the acute angle or the obtuse angle. But really what I got to do here is use my calculator and the inverse sine of 1.12653 and so on, because I got to get what that reference angle is. Okay, so it's second sine, second answer. Oh, well that's interesting, isn't that? The problem is I can't do that. Okay, I'm going to go back here a little bit. As soon as I did this calculation, this initial calculation here, see the issue is sine can't be a number bigger than 1. Sine is always the opposite side over the hypotenuse. Okay, the ratio is always the length of the opposite side over the hypotenuse there. And the hypotenuse is always the largest side in the right angle triangle. And so that means that the sine ratio must always be less than 1. This doesn't work. Okay, this gives me an error. And so what happened here is we run into the last possible situation here. Okay, there's no solution here. Okay, so we've seen the ambiguous case gave two possible angles that worked for that unknown angle. Okay, In the previous question that we just did, there was only one possible result because when I looked for that, the second version or the second option for that last angle, it gave me a negative result. That made no sense. So there was only one answer that worked there. Here, what's happening is we're getting no solutions. This isn't even describing a possible triangle. And actually, technically what's happening is we're seeing this. Okay, based on the information that we gave here, what you're doing is this is 50 degrees, this was 25. That other side there, that 17, wasn't even long enough to connect to the base of this triangle, or quote-unquote triangle, okay? So there's no solution. This isn't even a possible triangle that we're describing. So those are your three scenarios here. No solution, one solution, or as we saw on the previous page there, two solutions. All right, so now you've seen the three possibilities here. Let's just try another one here. So triangle ABC has angle A is 30 degrees, A is 5, B is 10. Let's just draw this out here. A, B, C. Okay, A is 30 degrees, little a is 5, little b is 10. We want to find angle B. Okay, again, we're looking for the angle. That's where the issues could pop up if they're ever going to pop up here. I know I'm using the sine law because I've got the side and the angle pair there. So 5 over the sine of 30 degrees is going to equal 10 over the sine of angle B. That's what I'm looking for. Perfect. Cross multiply. Okay, so here we go. Whoops. For a second there I lost the angle. I couldn't see there. And then the sine of B is going to equal 10 sine of 30 degrees over 5. Now, when you do this, go to your calculator, you're going to see an interesting result here. Now, not something that makes this different than what we've done before. Nothing crazy weird, but it's going to be a little different here. So 10 multiplied by the sine of 30 divided by 5, okay, is 1. So the sine of B is equal to 1. Now, you probably at this point don't even need the calculator to tell you what the result here is, but let's do it anyway. Okay, we're going to take the inverse sine of 1. Now, I already know that this could be in the first or second quadrant here. I'm just going to find the reference angle, and it's 90 degrees. Turns out that's a quadrantal angle. Okay, turns out this right here is a right angle triangle. The information that they gave us is such that actually this is the same old triangles that we've been doing since you started working on trig. Now, that's interesting because what that means is the sine law works not only for oblique triangles, it'll work for right angle triangles as well. Okay, which makes it a really, really useful tool, kind of a even more powerful tool than your regular SOHCAHTOA that you've been using up to this point, because it'll work for any triangle. All right, so this question here, sketch and solve the triangle. So now they're solving the triangle problem. Triangle KLM. Okay, here we go. KLM. Angle L is 46 degrees. Little l is 3, little k is 4. Okay. Now, I have got an angle side pair. Okay. So I'm going to use the sine law. And I know little k's, which means at this point here, the only thing that I actually can solve for is going to be little angle k. So that's going to be 3 over the sine of 46 degrees will equal 4 over the sine of k. Now, because it's the angle that we're looking for, and we've seen this before, we run into the possibility where there might be 1, 2, or even no solutions to this. So we just got to pay attention to that. All right, we cross multiply, so 3 times the sine of k is going to equal 4 times the sine of 46 degrees. And I'll divide by 3. So 4 sine of 46 degrees over 3. Now, you've already seen me do this a few times. So now what I'm going to do is I'm going to leave this into the calculator. I already know that this is going to give me two possibilities. It's either a first quadrant angle or a second quadrant angle. What I got to do is figure out how big that's going to be, and I'm going to do that by taking the inverse sine of whatever this turns out to be. So I'm actually going to do this all in one step. I just want you to see that your calculator can do this. So I'm going to take the inverse sine of, and it was 4 times the sine of 46, close brackets, divided by 3. And then I'm going to close brackets there. And what that parentheses right there is it's closing off this set of parentheses that the inverse sine opened. And when I press enter, I'm going to get, okay, 74 degrees. I'm going to round that to the nearest whole degree there, 74. Okay. Now in my calculator, I'm going to leave it the way it was written there. Okay. Now, I don't know, sorry, that's the reference angle. That's K. So K could have been 74 degrees, or it could have been, whoops, sorry, 180 minus that answer. It could have been 106 degrees. Now, I don't know. Do those both work? Well, let's just figure out here. Angle L is always going to be 46 because that was what was given to me in the initial problem. Now it's M. Okay, now I'm probably going to have to start from scratch here. So in this first case here, what would it look like if K was 74 and L was 46? Well, 180 minus 74 minus 46. Okay, and angle M could have been 60 degrees. Okay, well that actually works out just fine. What about that other scenario? 180 minus 106 minus 46. 28. Actually, those are okay. Okay, those are going to work out just fine. So there are actually two possible triangles that could satisfy this. So let's think about what I've done thus far. I found possible values for angle for K, and then as a result, I've also found two possible angles for angle M here. The only thing that I don't know right now is little m. Okay, but M could be either one of those, so little m could be one of two possible answers here. Now, I'm gonna use the angles that I just found here. I don't want to make this more complicated and leaving stuff in the calculator here, but I'm going to just quickly jump over this. So I'm going to set up the ratio here to find little m. So I know that 3 over the sine of 46 degrees, whoops, could equal little m over the sine, and to start off with, of 60. Okay? Once again, let's cross multiply. 3 times the sine of 60 is going to be little m times the sine of 46 degrees. And then I'll divide. Okay, it's going to equal little m. This is just calculator work, but we got to make sure that we're entering this in properly. So 3 sine of 60 divided by the sine of 46. Now bear in mind that that 60 wasn't exactly correct. It was a little off. So the answer that I'm about to give you here isn't going to be perfect, but this gives you an idea of what we are intending in this problem here. And so the answer here to the nearest tenth, at least at this point here, is going to be 3.6. So that's one value of m. If capital M is 60, if angle M is 60, side M is going to be 3.6. Or we could have done it like this. And then this would have been little m over the sine of 28. And again, cross multiply. It's going to equal m times the sine of 46. Then we divide. 3 times the sine of, whoa, I can't believe I wrote that. Sorry, 28, not 38. Over the sine of 46 degrees is equal to little m. And again, this is just calculator work. And actually, in this case right here, I can be kind of lazy about this. I'm going to just yank that down here and change that 60 to a 28. And now I get a side here of, well, if I round that to the nearest tenth, that's going to round that 9 up. I'm just going to round that to 2.0. Okay, so there you go. Okay, we've solved this triangle here. We've got two possibilities. K could have been 74 or 106, which means M could have been 60 or 28, which means finally M could have been 3.6 or 2.0. Okay, here's another one that says solve the triangle. So we got to find the pieces that we don't know. However, in this particular case here, notice that the very first thing that we're going to do here is look for that missing angle, because there's only one angle we don't know. And so if we subtract those both from 180, we're going to be left with 53 degrees. Now, that gives us no ambiguity at all about the angles. Like in the previous question, we had the ambiguous case of the sine law. There was two possible triangles that satisfied those conditions. Here we're not going to get that. So just for argument's sake, let's call this x, let's call this y here. So that's going to make this angle x, that'll make this angle, whoops, angle y. Oh, wow. Sorry, that's not true at all. That's going to make that y right there. Yikes, ignore that. So let's solve for maybe let's solve for side x first. So 32.5 over the sine of 49 degrees, because I've got that angle side pair. That's going to equal little x over the sine of 78 degrees. We are going to cross multiply. Multiplied by the sine of 49 degrees, and then we're going to divide. So 32.5 sine of 78 degrees over the sine of 49 degrees is equal to x. Okay, now this is just calculator work. Okay, so 32.5, whoops, 32.5 multiplied by the sine of 78 divided by the sine of 49. Okay, and there we go, 42.1. Whatever the units happen to be. So there's side x. Now we just got to solve for side y there. But we're going to start with that same ratio that we used to begin with. The other question, 32.5 over the sine of 49 degrees, because I know that. And then it's the angle 53 that I'm working with, so this is going to be little y over the sine of 53 degrees. Cross multiply, so 32.5 times the sine of 53 degrees will equal y multiplied by the sine of 49 degrees. We're going to divide. So always cross multiply and divide. Equals y. And now this is just, once again, calculator work. And I'm just going to go up and steal that last one that we worked on and just change that 78 to, what was it, 53. Press enter, and we get 34. Whoops, you can't even see that, sorry. I went up there and I just changed that 78 to a 53. And then we're going to get 34.4 units. And so there we go. We've solved the triangle. We've got the two sides that we were missing, and we figured out what the missing angle was. All right, now let's try a word problem here. So to calculate the width of the river, the following measurements were made by a surveyor, and then we're going to find the width of the river to the nearest tenth here. So what happens here is you got this surveyor, he stands here, he looks to some spot here, let's say there's a tree there, a beautiful tree. Looks over there and he takes his measurement, he measures that angle to be 74 degrees, and then he goes for a little hike, 250 meters, turns around and he looks back at that same tree and he measures this angle to be 60 degrees. Okay? So we know these measurements right here. So the question is, how wide is the river? Now, the first thing that we're going to do here is notice that the triangle that he's actually making here is not a right angle triangle. Now, when he draws that width right there, granted, yeah, we are creating two right angle triangles, but the larger triangle here isn't. And this 250 meters is going across, see, we've got those two little right angle triangles, but this 250 meters goes across both of them, and it's not cut in half. Okay, if this was an isosceles triangle, if this was 60 and this was 60, then yeah, that would be. But in this case, it's not. This is 74, this is 60. These two distances aren't the same. So what we're going to do here is we're going to, first of all, figure out what that missing angle is in this larger triangle. So we're just going to subtract 74 and 60, okay, from 180. And we're going to get that this angle up here is 46 degrees. Okay? Now I've got a side opposite that, 250 over the sine of 46 degrees. Now what I can do is I can figure out either one of these two sides here. So let's call this x, we'll call this little y. I can figure out either one of those two here. Now it doesn't really matter, so I tell you what, let's figure out what okay, I was pointing on this angle here. Let's figure out what x is. Okay, so little x over the sine of 74 degrees. Now we're going to cross multiply. So 250 sine of 74 degrees is going to equal x times the sine of 46 degrees, then divide. 250 sine of 74 degrees over the sine of 46 degrees is equal to x. And we get, okay, 250, I'm just doing it on my calculator off to the side here, divided by the sine of 46 degrees. I'm making sure to close the parentheses after the angles, press enter, and I am getting, rounded to the nearest tenth here, 334.1 meters. Now I'm going to leave the actual number that I got in my calculator here because I'm going to need that number in just a second. Okay, now that is the length of this side. Now what I really want is the distance straight across, the width here. So what I'm going to do is I'm going to ignore this and I'm just going to look at the right angle triangle that I've got. Okay, I know that this angle here is 60. I don't know what this angle is up here. The whole angle was 46, but I don't know what that other angle is. I mean, I could figure it out, but I know this angle is 60 without doing any work here. So to figure out what the width is, okay, the sine of 60 degrees is going to equal the width over x. But I know what x is. Okay, I already know what x is. Now, I'm going to write it out like this, as the sine of 60 degrees over 1 is equal to w over x. And the reason I do that is because I really, with trigonometry, man, I really like this idea of consistently doing this little bit of cross multiplication here. Okay? Now I'm looking for w. I know what x is. It's sitting on my calculator. So all I got to do with this x is multiply that by the sine of 60 degrees. And I get that w, or the width of the river, was 209.3 meters. Okay, that's the number that we were looking for. Right. So one more problem here. And in this question right here, our goal here is to figure out the side AB. But the information that I have, okay, is about this triangle right here, this ADC. And that ADC is not a right angle triangle. Okay, so what I got to do is I got to figure out, well, what do I know about this triangle ADC? I know this side right here, DC, that's opposite this angle. So if I'm going to use the sine law, I need this angle. But I don't know it. I know that this angle here is 70, which means I know what this angle is. Okay, if this is 70, this angle right here has to be 110 degrees. Okay, because those two angles together, ignoring everything else in this problem here, those two angles together have to add up to 180 degrees, that straight line. Now, if that's 110, adding those together, 110 and 40 degrees, that's 150. That leaves me with 30 degrees up here for angle A, which is great, because now I have enough information to do the sine law. I've got a side and the angle opposite it. Okay, now, ultimately, my goal is to get side AB, and I can see that it's part of a right angle triangle, or even a couple of right angle triangles, actually. So I just got to pick a side here. I don't know, maybe I'm going to solve for this one right here. Let's solve for side X, AD. And in this triangle here, this oblique triangle that I've got, ignoring that right now, that X is opposite that 110 degrees. So this is going to be X over the sine of 110 degrees. We cross multiply, so 15 times the sine of 110 degrees is going to be equal to x times the sine of 30. Okay, and then I'm going to divide, so 15 times the sine of 110 degrees over the sine of 30 degrees is going to equal x. Go to my calculator. Right? 15 times the sine of 110 degrees divided by the sine of 30 degrees. And I get that x is going to equal 28.2 to the nearest tenth. Now I'm going to leave my actual value that I calculated in there. I'm going to come back to that in a second. So now I know what that side is right there. Now I'm going to redraw this. Okay. And I'm going to throw in just the pertinent information that I need. I am looking for side AB. D, I know that this is 40 degrees, and I just figured out that this is 28.2, and I know that that's a right angle. This now reduces down to something that I can use just simple SOHCAHTOA for. Okay, There's my triangle. I am looking for the opposite side. Let's call this y. And I know the hypotenuse. So the sine of 40 degrees is going to equal y over 28.2. This is like the sine of 40 over 1. Again, I do that because I like doing the cross multiplying here. So this will be 28.2 multiplied by the sine of 40 degrees is going to equal y times 1. I have the actual value here, so I'm going to leave that in there. I'm going to multiply this by the sine of 40 degrees, and we get that y is equal to 18.1. Y, or that side AB. That was the side that we were looking for.